Welcome to this week's episode of Brainstorm, where we give you a glimpse into the world of science for Thursday, January 16th, 2014. We begin with news from the world of medicine. A group from the University of Washington has been developing a new type of vaccine that could be produced and distributed much easier than current technologies. Most vaccines are proteins or other molecules from the surface of a virus or bacteria mixed with compounds that stimulate the immune system. This prepares the immune system to recognize that disease sooner and fight it more effectively. While this is amazing, current vaccines do have some drawbacks. Normally, they are expensive and time-consuming to develop, not the easiest to produce on a large scale, and require refrigerated storage and transportation. This group was attempting to develop a much more simple method that would solve most of these problems. They created engineered proteins that both act like an antigen from the disease, like found in normal vaccines, but that also bind to calcium phosphate. Teeth and bones are mainly calcium phosphate, so this combination created nanoparticles that were safe to inject. As an added bonus, the calcium phosphate actually helped ferry the antigen proteins to the lymph nodes, where they could more effectively interact with the crucial parts of the adaptive immune system. Mice given the nanoparticles showed a 3 times greater immune response to the target disease, versus just the engineered proteins without the calcium. If this is shown effective in humans, the idea is that supplies of engineered proteins could be on hand for doctors, either dehydrated or freeze-dried. They would be easier to transport and only require mixing from water and calcium phosphate to form a supply of vaccine, allowing doctors to more readily administer vaccines in epidemic situations, especially in remote areas. Our next story is an update also from the world of medicine and featuring nanoparticles as well. Researchers from Harvard and MIT have developed a new approach for controlling transplanted cells that will hopefully be used in therapies. Right now, plenty of researchers are creating and manipulating cells in labs. This is relatively simple. If you can get a cell to grow in a culture, all you need to do is add the right compounds or drugs that make it act the way you want. This isn't normally possible if you try and transplant those cells into someone, because the cells then have to deal with all of the signals coming from the natural body environment. What these researchers did was come up with a relatively simple solution to this dilemma. They called it particle engineering. Basically, they can create nanoparticles with whatever drug necessary to get a desired behavior and allow the cells to internalize them. After transplanting, the particles slowly degrade and release the drug, only affecting the transplanted cells. So far, they've done some experiments with making stem cells differentiate and changing how foreign cells would react to the immune system. They think this technique can be applied to many cell therapy applications, including cancer, and hope that other groups will begin experimenting to accelerate the field as a whole. Finally, we have news from the world of materials science. A team from Duke University has developed a metamaterial that could make Nikola Tesla's dream of wireless electricity a reality. They created what is called superlens, which does not bend light but instead magnetic fields. It's an unassuming device that consists of hollow blocks with finely etched copper spirals in a repeating pattern. These interact with the magnetic field by essentially focusing it in a more intense but narrow cone emitting from the superlens. Very basic wireless power can be achieved with simple copper coil electromagnets. Putting electricity through one will generate a magnetic field that will induce a small amount of current in a nearby coil. The problem is, with a 1-inch coil, you barely get usable levels of energy transfer over 3 inches beyond. And this can be boosted by simply making the electromagnets bigger, or increasing the amount of electricity going into the transmitting coil. But either way, that quickly becomes impractical. However, by putting this metamaterial near the transmitting coil, it creates a directional magnetic field with a range of nearly a foot, so about 12-fold increase when using 1-inch coils. And this is just the beginning, as the team hopes to further develop it and make it practical for everyday uses such as charging mobile devices. Their next goal is to even develop a power transmitter that will turn to focus on a moving energy receiver. Well, hope you enjoyed this episode. What creative uses would you find for wireless electricity? Let us know your thoughts on that and all the stories in the comments.